Guys, welcome back to another video of CFS, and we are today doing DFS of a graph. Now I know you must be thinking that when we did BFS of a graph, we moved from BFS of a tree, we understood the level order traversal, and now we have suddenly moved to the DFS of a graph without doing DFS of a tree because I never put up the title that we are doing DFS of a tree, right? So what happened over there? Did we miss a topic? No, not really. So the interesting thing is that you already know DFS, you just don't know it. So all the tree traversals that we have been doing till now, the pre-audit traversal, the post-audit traversal, the in-audit traversal, it is all in fact DFS itself. So we will understand what is DFS exactly and how we have actually been using it already. I need one of you to quickly confirm that you can hear and see me properly. You are able to see the question that we're going to solve today and you are able to see the code as well. Okay, so what exactly? Hi Shivai, thank you so much for showing up again. I really appreciate that some of you really show up every day, although there are very less number of people watching the series, but I want to continue. I had committed 18 days and I want to finish the 18 days at least. So coming to the question that we are going to do today, DFS of graph. So we saw BFS of graph earlier, right? What is BFS? We were traversing the tree breadth wise, right? So basically level by level. So if this is one level, then this is another level, then this is another level. That is why the term was breadth first search. Now when we say depth first search, which is DFS, we mean that instead of going level wise, we are going to go down one branch, go back, come one branch, go back, come one branch. So basically we're going to go deep down one branch until we are done traversing all the nodes in that depth. Then we are going to go back, then come back, then go back. Okay. So actually if you see in trees, in pre-order, post-order as well as in order, that is exactly what we do. We go down one branch. It is just that whether we visit the root first, in middle or later, right? That is what we do. So all the traversals of trees that we have been doing so far, other than level order traversal, that is pre, post, in order, they were all basically DFS itself, which is going down one depth, coming back, going down one depth, coming back, going down one depth. Now coming to again DFS of graph, how will it be different from DFS of trees or basically in order, post order and pre-order? How will it be different? Here also the thing is in a graph we can end up having a cycle. That is the one thing that obviously that since there can be a cycle, we have to mark the nodes as visited. Otherwise, we'll end up in a loop. We'll end up visiting the nodes again and again. And whenever you are in a graph, whenever you are in a directed or undirected graph, so it doesn't matter. Here, see the previous example that we had taken for BFS, it was directed. Here it is undirected. It does not matter. It can still lead to a cycle, right? Suppose these two nodes were connected, it would have been a cycle unless it is given that it is acyclic graph. In that case, we don't need to check visited because in that case, we can't end up in a forever while loop. Here, we can end up in a forever while loop. That is why we need to put a check of the visited array. Is this much clear, guys? So much theory. Fine. Fine till now. So here, the vector here, how will we be visiting the adjacent elements? Here again, we are given that the adjacency list, right? So again, this is the adjacency list. Number of rows is we don't know the number of columns, just like we have been doing so far. Okay. Now the next question that comes, that in the BFS we were going level by level, right? So we were using what? We were using queue because we needed first in, first out. So the nodes that we visited first, we needed to visit the children of those nodes first. Here, what are we doing? Here we are going and then coming back, going and then coming back. Now you must be thinking that we don't really use any data structure in pre-order, in order, post-order, right? So does that mean that DFS does not require any data structure at all? No, that is not the case. In DFS, till now, actually we have been using a data structure by itself. I need one of you to tell me yourself that which data structure I have been using. Very good, Mansoor. So here we will use a stack. Why a stack? Because we have actually been using a stack already. When we do recursion, what do we actually do? We use recursive stack, right? You remember how functions keep storing the value one above the other. So we have actually already been using stack. It is just that instead of the stack data structure, we have been using recursive stack. And while writing today's code also, we are going to be using recursive stack itself. So obviously we need a separate recursive function. Now, why do we need a stack over here? Let's look at it once more. Because once we are done visiting all the nodes in depth, we need to come back. So whichever nodes were visited first. So here 0 was visited first, then 2, then 4. So 4 was visited last, but it is popped out first, right? Because I'm done visiting, then I'm done visiting 2, then I'm done visiting 0. So it is first and last out. The first node that was put in is going to be pushed out what? Last. So 0 is the node that was pushed in first, so it is the node that is going to be pushed out last. So these are differences between BFS and DFS. In BFS, we use a queue, it is level order reversal. In DFS, we use a recursive stack or a stacked data structure. It is first then last out. I hope you have understood till now. We are going to come to the code. If there is any doubt, feel free to ask me. I'm over here to help you out. So what do we need to do? We need to return a vector of integers. So I'm going to make a vector. I'm going to call it vector of int and I'm going to call it res. Now again, I need to mark my nodes as visited. So I need another vector of Boolean variables. I'm going to call it visited. What is the size? It is v. I'm marking initially all of them as false. Now in the question, it is given to us that we have to start from the 0th one, right? Perform a DFS, use a recursive approach from 0th vertex from left to right, right? So from the 0th vertex. So what am I going to do? I'm going to visit the 0th vertex first. So I'm first going to push it to my res, right? So we have to make sure that there is at least one node, right? Let us see. It is given that at least there is one node over here. See, I did not know this. When I was pushing it, I had to put a check that, okay, it should be there because they're saying from 0 to vertex, at least one vertex should be there. So just in case, I checked it out. Similarly, when you are using such cases, you should be discussing this with your interviewer, checking it out, okay, at least one route is there or not. Now, since we have pushed the 0th vertex, we are going to mark it as visited. Now, what am I going to do? In the end, first I have to return the res itself. But in between, I need the recursive function, right? So is my recursive function going to return anything? I don't really need it to return anything. I'm just going to call it DFS itself. So this is DFS of graph. I can call it DFS helper, DFS anything, right? I'm just simply calling it DFS. Okay, what are the things am I going to need? Obviously, I'm going to need the adjacency list. So I'm going to pass vector of int and the adjacency list. I'm obviously going to need the vector of the visited vector, which is how I'm going to mark my nodes as visited, right? I will always obviously need the resultant vector that I'm going to fill, right? Is there anything else that I need? Okay, so this is vector of both. I'm so sorry. Then what else do I need? I should be present at a particular index. So I need to pass that index or that integer at the node that I am at. Will I need v? I doubt if I need the number of nodes that are there. We'll check it out. Okay. Now what am I going to do is, so I am at currently, what does this x represent? I am currently at the node x. Now I need to go to the adjacent element of the x. So what am I going to do? For all the elements that are adjacent to x. So let's just call it adjacent element itself. And how am I going to visit all the adjacent elements? In the adjacency list at the value x, all the adjacency elements are going to be there, right? Now for each of the elements, I first need to check that they are not visited, because if they are already visited, then obviously I can't do anything. I have to put a check over there, right? So if they are not visited, what am I going to do? I'm going to first push them into the resultant vector that I have. So I am going to push it. What else am I going to do? I am going to mark it as visited because it was not visited earlier. That is why we are visiting it now. And what am I going to do? Now I have to go down deep, right? I have to go to the adjacent elements of this itself. So I'm basically exploring a depth, right? So I'm going to pass the values, the adjacency list, the visited vector, the resultant vector. And now what is my new x value? It is the element that I am dealing with. So if you see, whatever was the first element of this 0 would have been there. Then the first adjacent element, then the first adjacent element, then the first adjacent element, like this. From 0, what was the first adjacent element? Was 2. Then what was the first adjacent element? Was 4. Once we are done with 4, we will go back. Then the next adjacent element, we will go back. Then the next adjacent element. So we are going down one branch because the DFS is within the for loop. We are going to visit the next adjacent element only when this is done. Only then we are outside, right? So here I'm going to call this DFS function. What all do I need to pass? I need to pass the adjacency list, the visited, the res, and the initial one is 0. Let's compile this and see. I'm quickly looking at the comments if there are any questions or anything at all. Okay, so this works. Let's try to submit it. Sahil is saying no voice. I You guys just said that that you were able to hear. Can you just check once again that you are able to hear or not? Because I've been getting responses so far. So we have all the test cases as passed. Voice is correct. Thank you, Deepraj, for the confirmation. Let's look at the time and the space complexity. If you guys have any doubt till now, please let me know. Have you understood what is the difference between BFS and DFS? Have you understood why we are using a queue over there and how we are using a stack over here? It is a recursive stack that we are using. Have you understood that how we are visiting the adjacency elements, how we are going down one branch, how we are visiting depth-wise? If you have understood this much, you are actually done with DFS. It's a pretty tough topic and a very, very important topic because we're going to be doing so many graph questions related to this. It is super, super important. Okay. Now what to do? So the expected time complexity is what? Order of V plus E. Why is that? See, adjacency list, like in VFS, we are going to visit all the elements, which is V, and then the number of connections is what? E, that is the number of edges. So time complexity is order of V plus E, which is same as BFS. Auxiliary space also same as BFS, because here we are using the elements in recursive stack. There we were storing in queue. But again, the maximum number of elements that we can store is the maximum number of vertices that is there. So it is order of V. The constraint is 10 power 4. So order V plus E and order of V works. And I really hope you liked the question and you were able to understand. Thank you so much, guys, for showing up. Tomorrow we are going to be detecting a cycle in a graph. First, we'll do in a directed, and then in an undirected graph. So it is pretty interesting. I hope you will show up. These are really hard questions of graph, and kudos to you for showing up. Really, it means so much to me. So see you tomorrow. Please do practice. The link is in the comments, and I hope you will practice. See you. Bye.